In this chapter, we're going to look at another way that aldehydes and ketones can react. In a previous chapter, we discussed a type of reaction for aldehydes and ketones that involved attack of a nucleophile on the aldehyde or ketone carbon. Now we're going to look at a different way that aldehydes and ketones can react. In organic chemistry, we call these different ways of reacting modes of reaction. In this second mode, we're going to see that the carbon adjacent to the carbonyl carbon becomes more acidic than a typical carbon-hydrogen bond would be. We're going to start by going over a system to indicate the relative position of carbons to the carbonyl group. We're then going to look at this type of acid-base reaction on the adjacent carbon. We can use Greek letters to indicate the position in a carbon chain relative to a functional group. In this case, we're going to look at the C double bond O carbon as being the functional group. In that case, the carbon attached directly to this C double bond O carbon would be called an alpha carbon. The next carbon in the chain would be beta. The third carbon would be gamma, then delta, epsilon, and of course we can continue on, but typically we don't go much further than epsilon. These are the symbols that are used for these Greek letters, and they're summarized right here with their names transliterated into English. The hydrogens on the alpha carbons of carbonyls, which we call alpha hydrogens, are more acidic than hydrogens that are typically attached to carbon. For example, an alkane usually has a pKa of around 50, while the pKa of an alpha carbon of a carbonyl is much lower, somewhere in the neighborhood of 17 to 22. Remember that as the number gets smaller and approaches 0, the hydrogen becomes more acidic. Remember also that each change of 1 in the pKa number reflects a 10-fold increase in acidity. So we're looking at a change of over 10 to the 30th in the strength of the acid. We explain this incredible increase in acidity by looking at the stability of the conjugate base that would be formed after the acid-base reaction. Here's an acid-base equation that shows the hydrogen attached to the alpha carbon being deprotonated by a base. So in this case, this would be the acid. This would then form this conjugate base where the alpha carbon has a lone pair and a negative charge. We can see that the conjugate base has the possibility of resonance. That resonance stabilizes the conjugate base when compared to the conjugate base that would be formed if we didn't have the adjacent carbonyl. The resonance looks like this. We envision that the lone pair on the carbon pushes toward the adjacent carbon-oxygen pi bond. So it pushes down here to make room for it so that we don't have 5 bonds on that carbon. The pi bond pushes out onto the oxygen, giving us this resonance structure. In a sense, this is an allylic resonance structure, and we have seen that a shortcut to generating allylic resonance structures is to simply swap the double bond location and the location of the reactive intermediate, in this case, the lone pair and negative charge. So the double bond moves here, and the lone pair negative charge moves up to there. This resonance structure stabilizes the electron density in the enolate, thus making the original acid a stronger acid. There are 2 ways in which this stabilization occurs. First is resonance delocalization of the negative charge. We've seen that just having resonance structures will generally increase the stability of a species. Second, if we look at this additional resonance structure here, we can see that in this resonance structure, the negative charge is on an oxygen as opposed to being on a carbon. Oxygen is a much more electronegative atom. Therefore, that really helps stabilize that additional negative charge. So the combination of these two features make this much more stable than it would be if the negative charge and the lone pair were isolated on a carbon and unable to do resonance or delocalize.